But this technique, too, is limited. Only a few areas like Europe have long-term records which survive. To get a handle on the global climate, scientists have been forced to go beyond human accounts of the weather. "500 miles from the North Pole, a frozen lake will be home to a team of scientists for the next few weeks. It's part of an international effort to try and reconstruct the climates of the past.
We're here in the Canadian High Arctic on Ellesmere Island, about 500 miles from the North Pole. And it might seem strange that we would come to this kind of environment to study the problem of global warming. But what we need to do is to try to reconstruct the longer-term history of climate. And we do that by using so-called natural archives of climate, things that in some way retain in their structure a measure of how the climate has varied in the past.
Bradley and his team will spend the brief Arctic summer drilling through the ice and sampling the pristine sediments at the bottom of Lake Tuborg.
Because the lake is frozen over for most of the winter, what we have is a very brief period during the summer when the snow melts and the sediments are carried into the lake, and that settles out into the lake, and it forms these layers, just like the layers you see in a tree ring or in an ice core. Year by year, we get a nice sedimentary record.
These year-by-year variations in thickness will be used to estimate past temperatures at Lake Tuborg. A thicker layer means there was a warm spring, which melted more snow and produced more mud.
Wow, that's great. Look at this here. Wow, look at that.
This expedition yields temperature information going back hundreds of years, but in just one location. To estimate the past average global temperature, such measurements must be made all over the Earth's surface. 3,500 miles to the south, a team from Scripps Institution of Oceanography are examining the trees in Mammoth Park, California. Franco Biondi and his colleagues have done this many times.
The way the trees grow, they will cover themselves entirely every year with a new layer of wood. And if you take a horizontal section, you're going to see the width of each one of these layers.
Because trees grow all over the world, they are one of the most powerful natural recorders. Their annual rings not only give scientists a built-in date, they also contain a record of past temperature and precipitation.
Each one of these layers is an annual layer seen in cross-section. The annual layer is formed by these two portions together, the early wood and the late wood. And the width of the layer is our first indication of a climate pattern. So the narrow band that you see here indicates a year when the winter and spring were drier than normal, and then the larger layers that you see here indicate a period when winter and spring precipitation were more abundant than normal.
Trees are very common on land, but for the 3/4 of the planet covered by ocean, scientists need other recorders. Like trees, corals can live for hundreds of years and grow at different rates depending on the temperature at the sea surface. The Earth's temperature is also preserved in the chemistry of ice layers extracted from glaciers all around the world. Each natural recorder produces estimates of temperature and rainfall for a given place and time. Combining them all, scientists have been able to extend back the temperature record for the Northern Hemisphere about 1,000 years. According to this graph, published in 1999, the 20th century's 1-degree warming stands out dramatically. But what about Greenland and its controversial medieval warm period? According to the combined data, there was no medieval warm period. Specific regions like Greenland may have been warm, but the average global temperature back then was cooler than today. Even though the data is preliminary, Bradley is convinced the climate of the 20th century is unprecedented.
We think this warm period 1,000 years ago was just a regional anomaly. We find almost no period in that whole 1,000 years which has temperatures as high as we've seen in the last part of the 20th century. And in particular, the 1990s were exceptionally warm. It was an incredibly unusual decade, and we have no evidence that there was a decade quite like the 1990s all the way back 1,000 years.
If this finding holds up, does it prove humans are causing global warming? Some greenhouse skeptics like MIT's Richard Lindzen urge caution.
Well, it leaves out a couple of things. First of all, one has to distinguish the statement warming, meaning temperature has gone up, from warming, meaning man has caused temperature, or something has caused temperature to increase.
How can we be sure that recent warming is man-made rather than natural? And what evidence is there to link this temperature increase to human activity? Perhaps no man has done more to help answer this question than Charles David Keeling. 40 years ago, nobody knew for sure whether industrial greenhouse gases like carbon dioxide were increasing in the atmosphere or whether they were being absorbed by the oceans. In 1957, Keeling set out to discover which was right. Taking advantage of the special funding available in the International Geophysical Year, he set out with the latest analyzers to begin what would become his life's work.
This program afforded me an opportunity, even though I was just out of school practically and a very young man, to commandeer enough resources to see that these analyzers were put in several places, and rather quickly at that. One analyzer was put in Little America, Antarctica, and shortly after, another one was placed on a mountain in Hawaii called Mauna Loa.
The ideal place to measure carbon dioxide is away from cities which produce it, and distant from vegetation which absorbs it. On the Hawaiian mountain of Mauna Loa, Keeling found the ideal spot. Located at 11,000 feet in the midst of a barren lava field, he began to sample the Earth's air.
At Mauna Loa Observatory, we started the measurements in March 1957, and I expected the concentration would be perhaps almost dead constant, knowing nothing else as a hypothesis. But that wasn't what happened. The concentration rose for the several months, and then it dropped. And it dropped all during the period from May until September. And then it started to rise again. As soon as we saw that much information, less than a year's worth of data, it was pretty obvious that we were looking at the breathing of the plants in the northern hemisphere, because they absorb carbon dioxide during their growing period in temperate and high latitudes. And then it's released again in a cyclic process in the wintertime.
Keeling's sensitive measurements had picked up the Earth's respiration. Every spring, plants bloomed, sucking carbon dioxide out of the air. Every fall, CO2 was released back into the air as the plants decayed. But Keeling noticed that year by year, the total concentration of CO2 increased. Superimposed on the annual cycle was a rising curve. Each year, more CO2 was inhaled and exhaled by the biosphere. Over 40 years, the concentrations rose from 330 parts per million to almost 370 parts per million. The Keeling curve appeared to prove what many had suspected, that humans were changing the composition of the atmosphere. But why should adding an invisible, non-toxic gas be cause for concern? Compared to the major atmospheric gases, oxygen and nitrogen, the amount of CO2 is minuscule. But through an accident of physics, the greenhouse effect, its consequences are significant. Perhaps the most dramatic example of the greenhouse effect is the Earth itself. But for this effect, the Earth would be frigidly cold. Of the energy coming from the sun, about half of the light gets scattered and absorbed before it reaches the surface. The rest is radiated back as heat or infrared radiation. In the absence of a greenhouse effect, this heat energy would escape back into space, leaving the Earth with an average temperature of 0 degrees Fahrenheit. All water would freeze. The reason this doesn't happen is that greenhouse substances, gases like carbon dioxide and methane, and water vapor and clouds all act to trap escaping infrared radiation. The net effect is to cause the Earth's surface to warm up to an average of 59 degrees.
It's as real as gravity, and it keeps the planet habitable. We'd have an average surface temperature on the Earth below the freezing point of water were it not for the greenhouse effect.
But since the Industrial Revolution, there has been a new and growing source of CO2, fossil fuels like coal, oil, and natural gas. When fossil fuels are burned, their carbon atoms combine with oxygen in the air to make CO2. Every time we turn on a light or drive our cars, we are adding CO2 to the atmosphere.
It's hard for people to understand how much carbon dioxide is being put in the atmosphere in absolute terms, but in relative terms we can say as follows. At the end of World War II, about 1 billion metric tons of carbon in the form of CO2 was being emitted to the atmosphere. When I started my measurements, it had risen to 2.5. At the present time, it's almost 7.
According to the theory of the greenhouse effect, adding more greenhouse gases like CO2 to the atmosphere should cause the average global temperature to rise for as long as we continue burning fossil fuels. The climates of Mars and Venus were also shaped by the greenhouse effect.
Venus has an extremely high concentration of CO2 in its atmosphere, and it's blazing, boiling hot at the surface of Venus. And the Martian atmosphere, for instance, is very, very thin, and also within that thin atmosphere there's only a very, very small amount of CO2.